Hello everyone, in this video I explain experiment number 2, resistivity. How to find the resistivity of a copper wire. Let us start. The apparatus that we use to do this experiment is that power supply, ammeter, rheostat, variable resistor, switch, connecting wires, millivolt meter, digital, micrometer to measure the diameter of the wire, copper wire, it has 1 meter length. Now we start to find the diameter of the wire at 3 different positions.
Before using a micrometer, make sure the ends of the measuring surfaces are clean and that the micrometer is properly calibrated. Use a piece of paper or cloth and clean the measuring faces thoroughly. Check the calibration of the micrometer by using the ratchet to close the measuring ends and checking to see if the zero line on the sleeve is lined up with the zero line on the thimble. Use a spanner wrench in the small hole in the sleeve and turn the sleeve until both zeros line up. The line on the sleeve is graduated in millimeters. Every 5th millimeter is numbered from 0 to 25. Each millimeter is also divided in half. Turning the thimble in or out 1 full revolution moves it a half a millimeter. And 2 complete revolutions will move it in or out 1 millimeter. The beveled edge on the thimble is graduated in 50 equal divisions, and every 5th line is numbered. Each line on the thimble is 1/100th of a millimeter. To read the metric micrometer, first see how many millimeter lines are showing to the left of the beveled thimble edge. In this example, 15 millimeters is showing. Then see if there are any 5/10 millimeter lines between the beveled edge and the millimeters. In this example, there is 1 line, so 5/10 of a millimeter must be added to 15 millimeters. The last step is to read the thimble. Look at the thimble and see what number lines up with or is just below the line on the sleeve. In this example, the 6 mark is lined up with the line on the sleeve, so 6/100ths of a millimeter must be added. The total measurement is 15 and 56/100ths of a millimeter.
So start here. So it is half 0.5. So we have 0.5 plus the circle here 20. So the circle at 20. So it is 0.5 plus 0.20. So the diameter at the first stripe is 0.70. At the second position, we measure the diameter of the wire. So it is 0.5 plus 19.8. So 0.5 plus 19.8. It means 0.198. Okay. So we add them up by using the calculator. 0.5 plus 0.198. The answer is 0.698. The third one, okay, another place, 0.5 plus 19.5. So 0.5 plus 0.5, and then the circulation is 19.5. The answer is 0.695. All of this in millimeter. So this is the answer. Now what we do, we take the average. So we add them up, divide by 3, the average of diameter of the wire. The average is 0.698. This is the average of diameter. the length of the wire, it is 1 meter. So the length of the wire is 1 meter. Now we started to calculate the cross-section area of the wire before to do anything. How to do the cross-section area? First we find the radius. So the radius equals half the diameter. So it is 0.698 divided by 2. The answer is 0.349. So this is R. This is the radius of the wire. Now we find, this is in millimeter. So we change the radius from millimeter to meter, multiply by 10 power negative 3. So the answer is 3.49 times 10 power negative 7. So R equals 3.49 times 10 to the power negative 7 meter. Now we can get the area. Set up the circuit here. So we're starting from the power supply. First of all, we have to plug in the power supply and check is it working or not. Yes, it is working. And then switch off. We're starting from the power supply, from the positive. So we start. We take a wire from the positive power supply, from the positive pole, and type it. From the positive to the ammeter, to the positive. You have here in the ammeter 2 scales. We take down scale. It's up to 0.6 ampere. So each unit is 0.2. Each one dash is 0.2 divided by 10, 0.02 ampere. So we connect this down. So, and type it. Now we connect the ammeter. Now from the ammeter, now we take this away because we finished the micrometer. Now, from the other pole of the ammeter, because it follows each other, from ammeter to the wire. So I connect here to the wire. This is 1 meter exactly. And then from the wire to the rheostat, the variable resistor. You take a light wire. So from the wire to the rheostat. The rheostat has top and bottom. We connect one of them at the top and tighten it. And then the other one at the bottom. And then tighten it also. From the rheostat to the switch. So this is the switch. Okay, so we connect it to the switch. From the switch to the power supply. From the switch to the negative pole of power supply. Okay. So we connect to the power supply. Right. And then what we do? We check the connection. We check the connection. It's okay? We check the connection. So switch on. Power supply, and also, yeah, it is working here. Now we adjust the rheostat at 0 and then move it slightly. So the current increases. So now the connection is correct. So adjust it to 0 again. Switch off. Then what we do? We connect the millivolt meter in parallel with the wire. So we connect this one to this side. So we connect this one here. Okay, I check here. And the other one. This one. Now we adjust the millivoltmeter, it's digital. Okay, and now we check again, switch on. So, switch on, and let's see. Oh, it is in negative, so just we exchange the wires. So we exchange the wires. So this wire, exchange it. So this one here, and this one here. And we check again. Yes, it's working in the positive value. This is a millivoltmeter. So this one, 6.1. But you notice it is not balanced, not stable. So we're waiting to stable. So now the circuit is perfect. So what we do, we switch off the circuit. And now we adjust the voltmeter to 3 volt to don't overheat. Yeah, it's 4.5 volt. It's enough. We start to take the values. Let the current is independent variable. So just we change the values of the current and we find the corresponding value of the voltage. To switch on. And now we move this slightly. Yes. Now. So when you read the ammeter, you have to be in front. Take care for the parallax error. You have to look, okay, in front of the ammeter, direct to the ammeter. Now it is 5 dashes. 5 dashes, so we remove this. 5 dashes, and each dash is 0.02. So 5 multiply 0.02, so is here 0.1 ampere. So the first value is 0.1 ampere. 0.1 ampere. Now what is the corresponding value of voltage? So switch on. Now must be stable. 7.88. So it is 7.9. No, 7.98. So we write 7.9. Okay, 81. So it is 8. But this 8, it is millivoltmeter. So it's 8 multiplied by, it is 8 multiplied by 10 to the power negative 3 because it's millivoltmeter. So it's 8 multiplied 10 power negative 3 volt. Switch off again. So this is the first trial. Okay, the current is 0.1 ampere. The voltage 8 times 10 power negative 3 volt. Now we take trial. So we switch on and move it slightly. Yes. So this is 9 dashes. 9 dashes. So the current is 9 dashes multiply 0.02. So it is 0.18. So the current is 0.18 ampere. Now we find the corresponding value of the voltage. It is here. We have to stay to stable 14.5, 14.4, 14.6. So it is 14.5 at the middle. So it is 14.5 into 10 power negative 3 volt. Now we finish the trial. The 5 trials finish. So switch off the power supply. Now that are the results. For the length of the wire, it's 1 meter. For the average diameter is 0.698 millimeter. This is the average of reading by using micrometer. And we find the radius and we find the area. And then the trial. This is 5 trials. The current and the voltage. The current is independent and the voltage is dependent. Now what we do, we draw the graph. So first we draw a letter at the whole page and we write the title here. On x-axis, we represent the numbers in equal units, 0.02, 0.04, 0.06, and so on, till 0.18. On y-axis, it's up to 14, so we can say 1, 2, 3, but this is multiplied by 10 power negative 3. Now, this is y-axis, 0, 1, 2, 3, up to 15, multiplied by 10 power negative 3. Now we plot the points. What we do now, we draw the best fit line. It is a line passes in between and passes through the origin. That is the best fit line. That is the best fit line. Now we find the gradient of that line or the slope. The slope represents R because it's V over I. So we draw a big triangle. We find the slope of that line. The slope is y2 minus y1 over x2 minus x1. This is y2. We have to get it accurately. This is y2, 12.7. Down it is exactly 5. So this is y2 minus y1. So minus 5. But take care. We have to multiply by 10 power negative 3. Down it's x2 minus x1. x2 is accurate 0.16 minus. This is x2 accurate. x1 it is that one. After 0.06 with 1 dash. So now each unit is 0.02. 0.02 divided by 10. So it will be 0.002. So each 1 dash is 0.0, okay, 0 again. Each 1 unit on down is 0.02 divided by 10 dashes. So 0.02 divided by 10, it is 0.02. So each 1 dash on y-axis represents 0.002. So we add this to 0.06 because this point after 0.0. So we say plus 0.06. So that point is 0.062. Now from the graph we calculate the slope. It is 0.079. That slope represents the resistance. Now we go back to the paper and we continue. Plot the graph. Already we finished. We plotted the graph. Determine R from the graph. So R equals 0.079 ohms. So this is the resistance of that wire. Now calculate the cross-section area. We calculated before at the beginning the cross-section area. It was 3.82 times 10 power negative 13. So the cross-section area it is 3.82 multiply 10 to the power negative 13 meter square. Now this is a cross. Calculate the resistivity. Now for the resistivity, we know that R equals rho L over A. Rearrange this formula so we can get rho. So rho equals A R over L. So this is the resistivity. R times A divided by L. So for this value, rho equals, the cross-section area is that value, 3.82 into 10 power negative 13 multiply R, the resistance, 0.079 divided by L, the length of the wire, it is 1 meter. Now we calculate this value. We said compare your calculated value of rho to the actual value 1.6. We divide. When we compare, we divide the big value by the small value. We check the area because we made a mistake here. This is the squaring of this value. So just we recalculate here the cross-section area because we have mistake. So this is the cross-section area. It is 3.83 times 10 power negative 7, not 10 power negative 13 like we did before. Take care for calculation. So now this is the answer, 3.83 times 10 power negative 7. So the area here is, so the area equals 3.83 into 10 power negative 7 meter square. So this is the cross-section area. Now we substitute here. So it is 3.83 multiply 10 to the power negative 7. So this value multiplied by the resistance that we got before. So this value multiplied by 0.079. So this is the answer. It is 3.02 multiply 10 to the power negative 8 ohm meter. So this is the value of resistivity that we calculated. It is 3.02 multiply 10 power negative 8. Now we need to compare this value with the actual value. So how to compare? We divide. So the answer is 1.8. So our value is more than the actual value by 1.8 times. What are the sources of error in this experiment? Now, the sources of error may be here the losing of connection. This is one source of error. Also, the millivoltmeter is not stable, so the value is not more accurate. Also, parallax error for reading the ammeter. Sometimes overheat, so that are sources of error. So you can write any one of this. So the losing of connection through the wire. Also the wire has resistance, so we can say this is a source of error. The connecting wire, the connection wire has resistance, so don't only this resistance, we have another resistance for the connection wire. So losing current, for example, and also parallax error for measuring the ammeter. The millivoltmeter is not stable. Also another source of error, best fit line. Best fit line. Okay, maybe the calculation, we approximate a calculation in between. So that are the sources of error. For the conclusion, what do we write in the conclusion? Just we write the aim of this experiment, why we did this experiment, to find the resistivity of the copper wire. So by connecting the circuit, we will get the resistance of the copper wire from the graph. By knowing the resistance of the copper wire and the cross-section area and the length of the wire, we can calculate the resistivity from the relation R rho equals AR over L. And our value is more than 1.8 more than the actual value, because error in doing experiment, okay, but our value is approximately correct. Thank you.